Let's go ahead and practice finding the GCF of two given numbers using two specific strategies. I know there's other strategies out there, but in this one we're going to focus on using the prime factorization method. So we'll go ahead and do each problem using that method as well as the latter method to give you a lot of extra practice so you feel a lot more confident on how to use these two together and how they're related. All right, so for number one, we have this 12 and 9. I'm not going to make the factor trees in this video, so if you need to refresh that, go ahead and watch a previous video. But I know the prime factorization for 12 is going to be 2 times 2 times 3, and the prime factorization for 9 is just going to be 3 times 3. So using the prime factorization method, you just look at which prime factors they have in common, and it looks like they only have 3 here in common, so we know the GCF is equal to 3. It's as simple as that. That's the biggest factor, or the greatest factor, that goes into 12 and 9. Now for the latter method, you go ahead and just put the numbers next to each other, 12 and 9, just like this. And you can think of any two numbers, or any one number rather, that goes into both of these. And I'm going to say that 3, surprise, surprise, is the only number that goes into both 12 and 9. Right? So 3 goes into 12 4 times, and 3 goes into 9 3 times. And then you can see that 4 and 3 have nothing in common besides 1. So if you look at this 3 on the side here, this 3 actually matches the GCF. So you can notice here that the GCF of 3 is this one number that's on the side here. If you have more than one number on the side, then you go ahead and just multiply them together. All right. Something else to kind of notice here is if you look at the numbers that we didn't say that they were in common, this 2 times 2, that does equals this 4 here. And then this 3 that's left over here is this 3 that's left over here. So the number on the side is going to be the GCF for the latter method. For number 2, we have the numbers 12 and 8. So just like in number 1, the prime factorization for 12 stays the same as 2 times 2 times 3. And the prime factorization for 8 is going to be 2 times 2 times 2. So what do they have in common? Well, they both have a 2 and they both have another 2. So if you multiply 2 times 2 together, we're going to get the GCF is equal to 4. 4 is the greatest factor of 12 and 8. Now using the latter method, we can put 12 and 8 next to each other. And let's just say you didn't know that you can put 4 into both of these and you only could think of 2. Well, 2 goes into 12 6 times and 2 goes into 8 4 times. Then you just keep adding more steps to this ladder and you look at 6 and 4. Well, we think that they're both even, so 2 times 3 is 6 and 2 times 2 is 4. So if you look on the side here, the 2 and 2 multiplied together do get us the 4 that we were looking for because we knew the GCF was 4. Okay. Again, if you could do it in one step, you can make one step with the ladder and put a 4 instead, but I was just showing if you use 2. The leftover number for 12 is the 3, which matches this 3, and the leftover for 8 is this 2, which matches this 2. Cool. So they do line up, and you can see how maybe they are related to each other. For number 3, we have 18 and 15. So 18's prime factorization is 2 times 3 times 3. And 15's prime factorization is going to be 3 times 5. Now, what do they have in common? Well, they both have a 3 in common, okay, and I think that's it. So the greatest common factor for 15 and 18 is just 3. That's the biggest number that goes into both. Let's go ahead and confirm that using the latter method. So we have 18 and 15. I think the only thing I can think of is 3, which makes sense. 3 times 6 is 18, and 3 times 5 is 15. And 6 and 5 have nothing in common, so this number on the left side represents our GCF. This 3 does match this 3. And you can also notice here that the leftover numbers 3 times 2 is going to be the 6 underneath the 18, and this 5 that's left is this 5 over here. So we can see some similarities. For number 4, we have 8 and 6. 8 we've already done the prime factorization for in a previous one. That's 2 times 2 times 2. And 6 is just 2 times 3. So pretty short prime factorizations. They both have a 2 in common, and I think that's it. So the GCF, or the greatest common factor, is going to be 2. If we go ahead and write the latter method out, 6 and 8, they both are even, so I know we can divide them both by 2. So 2 times 4 is 8, and 2 times 3 is going to be 6. And so 4 and 3 have nothing else in common, so this 2 on the side must represent our GCF. And again, these extra 2's combine to make 4 if you multiply them. And this extra 3 is this extra 3 over here. Let's check out number 5. For number 5, we have the numbers 20 and 15. So for 20, the prime factorization is going to be 2 times 2 times 5. And for 15, the prime factorization is going to be 3 times 5. Now, what do they have in common? I think they only have the 5 in common, so that's the GCF. The GCF, the greatest common factor, is going to be 5. It's the biggest number you can split 20 and 15 into evenly. Now, if we go ahead and use the ladder method for 20 and 15, if you know your divisibility rules, you know 5 is the only thing that can go into both, and 5 times 4 is 20, and 5 times 3 is 15. So this 5 on the side does match the GCF that we got earlier, so that works, okay? This 2 and 2 on the side matches, and this 3 matches. For number 6, we have 24 and 18, so for 24, we know that's gonna be 2 times 2 times 2 times 3. And for 18, we're gonna have 2 times 3 times 3. And we've already used 18 earlier, so hopefully that prime factorization matches the one we did earlier. Now, they do have a 2 in common as a prime factor as well as a 3. So what is 2 times 3? That's equal to 6. So the greatest common factor for 18 and 24 is going to be 6. Now for the ladder method, you put 18 and 24 next to each other. And again, you can put whatever number you can think of that goes into both. I think of 6 right away because I know 6 times 4 is 24 and 6 times 3 is 18. And I know 4 and 3 have nothing else in common. So this 6 over here is going to check out and match with the 6 that we got. Again, if you use 2 and 3 separately, that's also perfectly fine. The 2 2's here multiply to get the 4, and this 3 multiplies to it by nothing, and it's still just going to be 3. So just little ways to check to make sure you're doing this correct. For number 7, we have 45 and 27. So 45 breaks down into 3 times 3 times 5, and 27 is going to break into 3 times 3 times 3. Now what do they have in common? They both have a 3 and they both have another 3. So I think that's it. So what is 3 times 3? 3 times 3 is equal to 9, so the greatest common factor is 9. If we go ahead and write these next to each other, we have 45 and 27. If you could think of 9 right away, 9 times 5 is 45 and 9 times 3 is 27, then you would be done. And if you did it in 2 steps and used a 3 and a 3, that would have been okay. This 5 and this 5 is good, and this 3 matches this 3, so everything checks out. For number 8, we have 40 and 30. Okay, so 40's prime factorization is going to be 2 times 2 times 2 times 5, and 30's prime factorization is going to be 2 times 3 times 5. Now you can see they both have a 2 in common, they both have a 5 in common, and I think that's it. So the GCF here is going to be 2 times 5, or rather we can say it's 10. And we can check this using the ladder method by 40 and 30, put them next to each other. If you can think of 10 right away, wonderful. 10 times 4 is going to be 40, and 10 times 3 is going to be 30, and the 4 and 3 have nothing in common. If they're one apart from each other, they never have anything in common. This 10 that we just got on the side does match this 10 over here. These 2 2's that were extra matches the extra, and this 3 matches the 3. All right, let's try number 9. For number 9, we have 24 and 16. So 24, the prime factorization is going to be 2 times 2 times 2 times 3. And for 16, the prime factorization is going to be 2 times 2 times 2 times 2. And so what do they have in common? Well, they both have a 2, they both have another 2, and they both have a third 2. So 2 times 2 is 4, then 4 times 2 is going to be 8. So the GCF here is going to equal 8. All right, using the ladder method, we have 24 and 16. If you were able to start with 8, then great. Maybe I'll just practice showing you what if you thought of only 4 first. So 4 times 6 is 24, and 4 times 4 is 16. Then you make another step of the ladder because 6 and 4 still have a common factor of 2. And 2 times 3 is 6, and 2 times 2 is 4. But now that 3 and 2 are right next to each other, they can't have anything in common. So then this 4 times 2 on the side is going to get you the GCF of 8. And so you can see 4 times 2 does get you 8, and that checks out. Of course, this 3 should match this 3, and this 2 should match this 2. For number 10, we have 16 and 9. So for 16, we just wrote its prime factorization, so we can just go ahead and copy that. Or if you have it memorized, that's also good. 9 is just 3 times 3. And for this one's pretty interesting. They have nothing in common. So if that's the case, you can go ahead and say that the greatest common factor is 1. Don't say that they don't have anything in common. Every number has 1 as a factor. All right. Same thing if we're using the ladder method, 16 and 9. And you're looking at these and you're like, I really can't think of anything they have in common, which makes sense because if you look at their prime factorizations, they have nothing in common. You just go ahead and put a 1 on the side here and say, well, 1 goes into everything. So we're going to go ahead and write 1. And this 1 over here is going to match. So this 1 matches this 1. Then it turns out like everything here is kind of an extra, which is why we're still left with the original. And then everything here is an extra as well, which is the 9. Okay? So if you don't find anything, don't say there's no GCF. There's always a GCF of 1 if you can't find anything at all. For number 11, let's see what we got. We have 20 and 28. So for 20, that's going to be 2, 2, and 5. And then for 28, we have 2 times 2 times 7. Okay, so what do they have in common? They both have a 2 and they both have another 2. So the GCF is going to be 4. Okay, now for the ladder method, we have 20 and we have 28. And let's go ahead and see, that's going to be, I'm thinking 4 right away, because I know 4 times 5 is going to be 20 and 4 times 7 is 28. 5 and 7 have nothing in common, they're both prime numbers. So this 4 does match the 4 that we got. And if you use 2 2s, that's fine too. 5 checks out with the 5, 7 checks out with the 7. For number 12, we have 21 and 14. So for 21, I think that's just going to be 3 times 7. And then for 14, I think that's just 2 times 7. And what do they have in common? Well, they just have these 7s in common, that's it. So that's the greatest common factor. The biggest number, you can split them into evenly. So for 21 and 14, go ahead and put them next to each other. 7 goes into both. This one 3 times, this one 2 times. And we are done. That's the GCF, 7. This checks out. This 3 also checks out. And the 2 makes sense. For 13, let's see what we got here. We have 15 and 25. So for 15, that just breaks into 3 times 5. And then for 25, let's break that into 5 times 5. All right. What do they have in common? They just have these 5s in common. That's it. And so we can go ahead and say the GCF is going to be 5. As for the ladder method, we have 15 and 25, put them next to each other. They both have a 5 in common, so 5 times 3 is 15 and 5 times 5 is 25. So I can't think of anything else, so this 5 must be the GCF, which it does match. The 3 matches here and the 5 as well, so 5 must be the greatest common factor. For number 14, we have 30 and 45. For 30, we have 2 times 3 times 5. We've already done that one. And 45, we've already done as well. It's going to be 3 times 3 times 5. So let's see what they have in common. They both have a 3 here, and they both have a 5. So the greatest common factor for 30 and 45 is going to be 15. Now, if you go ahead and use the ladder method, 30 and 45, maybe the first thing you think of is using a 5, that's fine. 5 times 6 is 30, then 5 times 9 is 45. Then you look at the 6 and 9 and think to yourself maybe 3. 3 times 2 is 6, and 3 times 3 is 9. And so if you multiply 5 times 3 on the side here, you do end up getting this 5 times 3 equals 15. Then this 2 matches, and the 3 matches. So we are confirmed that the GCF is 15 here. For number 15, we have 28 and 42. So for 28, I think we've already done, that's 2 times 2 times 7. And 42 is a new number for us, but I know that's 6 times 7, but 6 breaks into 2 and 3. So 2 times 3 is 6, and then we have a 7. Okay. Now, what do they have in common? They have a 2 in common and a 7 in common, and that's it. 2 times 7 is 14, so we know the GCF is 14. If you're using the ladder method, 28 and 42, most people would probably choose 7 first here. 7 times 4 is 28, and 7 times 6 is 42. And because they're both even numbers, I think people would choose maybe 2 here, so 2 and 3. And so if you multiply the 7 and 2 on the side, that does get you 14. which gets you the GCF. Then this 2 that is left and the 3 that is left makes sense. For 16, we have 32 and 25. So 32 breaks down into 2 times 2 times 2 times 2 times 2. And then 25 breaks into just 5 times 5. All right, so they have nothing in common here. So what do you remember from earlier? Hopefully you can kind of remember that if they have nothing in common, we should say the GCF is equal to 1. All right, if we go ahead and write the ladder method, you're gonna get the same thing here. They have nothing in common. So we're gonna put a 1 on the side and put 32 and 25. So this is the only thing they have in common, this 1. That checks out. Nothing here was in common, so these are all extras. So the extra is just all 32, all the entire thing. And these 5 and 5 combine and make that 25. Let's check out 17. So for 17, we have 10 and 35. So 10's prime factorization is just going to be 2 times 5. For 35, I know that breaks into 5 times 7. And so what they have in common here is just the 5. So I think that's our GCF. GCF equals 5. Now using the ladder method, we have 10 and 35. And I think they just have the 5 in common. 5 times 2 is 10 and 5 times 7 is 35. So this 5 here checks out with what we were looking for. And this 2 and the 7 also makes sense that they are not used or they're extra, okay? For number 18, we have 16 and 30. 16 is gonna be 2 times 2 times 2 times 2. And for 30, we have 2 times 3 times 5. Now, they both have a 2 in common, and I think that is it, right? So they only had one thing in common, which is that 2. So that's the GCF. For the ladder method, if we do 16 and 30, we should only find a 2 in common because we just did it using the prime factorization method. 2 times 8 is 16 and 2 times 15 is equal to 30. 8 and 15 have nothing else in common, so this 2 makes sense for the GCF. 2 times 2 times 2 does get us 8, and then 3 times 5 does get us 15. For 19, we have 60 and 45. So 60 breaks into, I believe, 2 times 2 times 3 times 5. And 45, I think, breaks into 3 times 3 times 5. Okay, so as these numbers maybe get a little bigger, sometimes you may need to use the factor trees or use a calculator to help you divide down a little bit, but try to use your divisibility rules to help you do so. Do notice that these 5s match as well as these 3s. And I think that's it. So what is 3 times 5? That's 15. So that means the greatest common factor here is 15. If you're doing 60 and 45, I'd probably say that most people would just say 5. That's a divisibility rule that most people kind of see more easily. 5 times 12 is 60 and 5 times 9 is 45. Then looking at this 12 and 9, you might notice they both have a 3 in common. 3 times 4 is 12 and 3 times 3 is 9. And so if you multiply 5 and 3, that does get you the 15 that we're looking for. And then the extra 2 2's multiply to get 4. And this extra 3 checks out as well. Let's see, we have 63 and 42. So let's see, 63, that's gonna break down into 3 times 3 times 7. And for 42, we've done earlier, so if you remember that one, that's really good. It's gonna be 2 times 3 times 7. Looks like they have a 3 in common and they both have a 7 in common, so what's 3 times 7? It's 21. So the GCF here is going to be 21. Checking this using the ladder method, 63 and 42. Let's see, I think most people are gonna think of 7 first because 7 times 9 is 63 and 7 times 6 is 42. And then for 6 and 9, I think 3 makes sense. 3 times 3 is 9, 3 times 2 is 6. And so if we look at what they had in common, it's this 7 times 3, which is 21. So that matches. And then this leftover 3 and 2 seem to check out as well. So pretty confident that the GCF here is 21. For number 21, we have 36 and 24. 36 breaks into 2 times 2 times 3 times 3. and 24 breaks into 2 times 2 times 2 times 3. Now what do they have in common? They both have a 2, they both have another 2, and they both have a 3. So what is 2 times 2? That's 4. And then 4 times the 3 gets you 12. So the GCF here is going to be 12. Now going ahead and using the ladder method, I think a lot of people would maybe think of 6 first. 6 times 6 is 36, and 6 times 4 is 24. Put another step on the ladder. Then 6 and 4, they're both even, so I think people would choose 2. 2 times 3 is 6, and 2 times 2 is 4. And so if you multiply the 6 and 2 on the side, 6 times 2 is 12, which matches over here. And then you get the leftovers, which seem to check out as well. So if you like the ladder method, use the ladder method. You can use the prime factorization to check it. If you like the prime factorization and do that, you can use the ladder method to check it. Up to you. For 56, I know that's 7 times 8, and I know 8 breaks into 2 times 2 times 2. And then for 42, I know that's 6 times 7, but 6 breaks into 2 times 3. And so what do they have in common? They both have a 2, and they both have a 7. So the GCF here, 2 times 7 would be 14. Turns out 14 is a common factor between 56 and 42. It's the greatest common factor. So let's see, if you use 56 and 42 using the ladder method, I would say that most people would probably choose 7 first, because 7 times 8 is 56, and 7 times 6 is 42. And what do 8 and 6 have in common? Well, they're both even numbers, so half of that is 4 and half of that is 3. And 7 times 2 on the side here is 14, which matches here. 2 times 2 does get you 4, and 3, of course, is 3. For 23, let's see what we have here. We have the number 80, so that's a bigger number. Let's see, I think it's 2, 2, 2, 2, and 5. And then for 48, I think that's going to be 2 times 2 times 2 times 2 times 3. Again, I've done so many of these, I just can do them in my head, but I know that's not the same for everybody, so it's not supposed to be a weird flex or anything. It's just if you want to get these prime factorizations correctly, go ahead and just make sure you actually make the factor trees until you get better at them. But every number's prime factorization stays the same. I've just done this way too many times. The 2's match here, another 2's match, another 2's match, and another pair of 2's rather match. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So the GCF here is going to be 16. Again, feel free to pause, take your time to write those out if you need more time to think. But that's the nice thing about here, you can kind of pause and think things through as you need to as well. So for 80 and 48, I'd probably say most people would think of 8 first, because 8 times 10 is 80, and 8 times 6 is 48. And then for 10 and 6, they're even, so people would choose 2. 2 times 5 is 10, 2 times 3 is 6. And so 8 times 2 on the side, that gets you 16, which gets you the 16. And then the leftover numbers seem to check out as well, the ones that were not used, or the uncommon prime factors. For 24, we have the number 20 and 72. So 20 is equal to 2 times 2 times 5. And for 72, I believe that's going to be 2 times 2 times 2 times 3 times 3. Again, feel free to pause to check that if you need to, or to write it out. That's definitely something you want to be pretty good at. And then they have these 2 2's in common. I think that's it. 2 times 2 does get you 4, so the GCF here I think is 4. Then for the ladder method, we put 20 and 72. And to be honest, I think most people would choose 2 here. 2 times 10 would be 20, and half of 72 is going to be 36. And then I think people would choose 2 again. 2 into 10 5 times, and 2 into 36 18 times. And so I think that would be probably the path that most people would take. 2 times 2 would be 4. And so this 4 that you multiply matches over here. This 5 is the leftover. And then 2 times 3 times 3, you can check that, but I promise that's 18. Here's 25. For number 25, we have 42 and 49. So 42 we've done a few times now. That's going to be 2 times 3 times 7. Feel free to look back for that one. And for 49, that is just 7 times 7. So right away, hopefully we can see that they only have the 7 in common. So the GCF here would equal 7. All right, if we go ahead and write these next to each other, we can use the ladder method. 42 and 49, they only have 7 in common. 7 times 6 is 42, and 7 times 7 is 49. This 7 is going to be the GCF, and that matches and checks out with the 7 we have here. And 2 times 3 does get you 6, and 7, of course, is 7. For 26, we have 11 and 44. 11's prime factorization, well, 11's prime, so just keep it the same. And for 44, that is 2 times 2 times 11. All right, now if we look at these numbers here, we can see that this 11 and 11 match, little squiggly there, and that's the only thing they have in common, so the GCF is 11. That always will happen if one of the numbers is a factor of the other one, or 44 is a multiple of 11, so the GCF would just be the smaller number. Okay, so we have 11 and we have 44. This ladder is going to look very short. It's going to have 11 on the side, a 1 on the bottom, and a 4 over here. So this 11 is just going to be the GCF. And then for 11, there's nothing left. So there's technically an invisible times 1 here, right? Because anything times 1 is the same. So if there's nothing left, it's always 1. And then 2 times 2 gets you this 4. For 27, we have 17 and 34. 17's prime factorization is just 17 because it's a prime number. And then 34 is even, so it actually breaks into 2 times 17. And so, surprise, surprise, they do have a 17 in common. So if we go ahead and circle the 17 with the 17, then the GCF we can see is 17. It's similar to 26, where the smaller number happens to be the GCF just because 34 is a multiple of 17, or 17 is a factor of 34. So using the ladder method, 17 and 34, we can see here the only thing they have in common, if you were to look, is going to be 17. That's going to be a 1 and a 2. And so the 17, what they have in common matches. There's an invisible 1 here. If you never see the number, put it there. And then the 2 matches the 2. For 28, we have 17 and 35. So for 17, we actually just did this. It's prime. And in 35, we have 5 times 7. I think that's one we've done already as well. They have nothing in common here, so we can go ahead and say the GCF is 1, because when I say they have nothing in common, they have no prime factors in common, so the GCF is just going to be 1. For the ladder method, 17 and 35, we go ahead and look and see if we can find anything, and you will end up saying that there's nothing in common, so you just have 17 and 35. So the GCF here is going to be 1, and so this one matches this one. The 17 that we weren't allowed to do anything with stays the same, and 5 times 7, we're not paired up at all, so that's 35. For number 29, we have 52 and 39. So 52, turns out it breaks into 2 times 2 times 13. You might need a factor tree again. 39 actually breaks into 3 times 13. So these 13s were hidden inside as common factors. I think that's all they have in common, so we can say the GCF is equal to 13. If we take this 52 and a 39, see what they have in common. If you were to look and think about it, then you'd eventually find out 13, hopefully, but this one's a little harder to see, so sometimes you might want to use the prime factorization method, and sometimes you're going to want to use the ladder method, but in this case, maybe prime factorization would be a little bit more clear to more people at least. But 13, I would say that 13, the multiples of 13 people don't know as commonly, but maybe you do, I don't know. This 13 matches this 13, this 2 times 2 gets you this 4, this 3 matches this 3. All right, for number 30, we have 90 and 54. For 90, that's going to be, let's see, I think that's going to be 2 times 3 times 3 times 5, okay? And for 54, I know that's 6 times 9. The 6 breaks into 2 and 3, and the 9 breaks into 3 and 3. So I believe that's going to be 2 times 3 times 3 times 3. And if we go ahead and see what they have in common, they both have 2s, they both have 3s, and they both have another pair of 3s. So 2 times 3 is 6, and 6 times 3 is 18. So I believe the GCF here is going to be 18. All right, so we have 90 and 54. What if we were using the ladder method and you like that one more? You'd probably think of 9 first. If you like the ladder method, 9 times 10 is 90. 9 times 6 is 54. So if you know like your bigger multiplication facts, usually you might like this one more. Then 2 goes into both of these because they're both even, so 5 and 3. And I think that's it. So 9 and 2 here do make 18 if you multiply, and that matches. And then the 5 checks out with the 3. Alrighty, for number 31, we have 64 and 72. For 64, this one's a lot of 2's. 1, 2, 3, 4, 5, 6. And then for 72, I know that's 3 2's and 2 3's. All right, so these have a lot of prime factors multiplied together. So they both have a 2, they both have another 2, they both have a third 2, and I think that is going to be it. Okay, so 2 times 2 is 4, and 4 times 2 is 8. So we can go ahead and say the GCF here is equal to 8. So that would be a lot of work to write those prime factorizations out, right? So what if we wanted to use the ladder method? If you knew your 8 times tables, then you'd probably be able to say 8 first here, and you'd be left with 8 and 9. And 8 and 9 have nothing in common because if they're 1 apart, they can't. And so this 8 here matches. So again, in this case, maybe the ladder method is the better way to kind of go. Or you can use prime factorizations if you feel more comfortable. So there are 2 methods that work better for different people in different cases. Finally, for number 32, we have 13 and 78. 13 is a prime number, so easy peasy. That's 13, and then 78, I think we can take half of that, so we can divide it by 2, that's 39. Divide that by 3, so it's gonna be 13. So we have 13s as our common prime factor. I think that's it. And so the GCF here is going to be 13. For the ladder method, we'll take 13 and 78. We'll go ahead and pair those up and say, well, think about what might go into both. 13's prime, so you'd have to look at the factors of 78. So in this case, I don't know, this one might be tough to use the ladder method for a lot of people, but it would be 13 times 1 and 13 times 6. And 13 happens to be the prime factor that they had in common, so that makes sense. For 13, that's times 1, so that's here. And 13 times 6, or 2 times 3 is 6, times 13 is 78. So there you have both methods for 32 different practice problems on finding GCF. And if you were able to, get a lot of these correct, then I think you should be in good shape for finding the GCF of 2 numbers. Hopefully you found this video helpful. If you did, consider giving the video a thumbs up and letting me know in the comment section down below which method you like more. And as always, keep up the fantastic work you're already doing, and I'll see you in the next one.